Hi everybody, welcome to my first video lesson. Bear with me, this is going to be new for all of us. So what I'd like to discuss today is the nature of light in the electromagnetic spectrum. So I'm going to go through the presentation and do a couple of examples along the way. So let's get going. Alright, so the first question I ask is, what is light? One of the earlier physicists to try to answer this question was Christian Huygens. He proposed that light was a wave because it underwent interference like other waves. So here on the screen, you'll see some actual interference patterns created by special sources of light. And since waves were the only thing we knew that would undergo interference, Christian Huygens says light is obviously a wave. Well, someone who disagreed with that perspective was my dear old dead ancestor Isaac. Now, Isaac proposed that light was actually a particle because it traveled in straight lines and bounced off surfaces much like a particle does. So if you take a look at the diagram here, I have a particle here and I will let it move, and we see that it travels and bounces straight off the surface. Just as light rays will strike a flat surface like a mirror and reflect off. So which is it? Who is right? Is light a wave or a particle? Well, it turns out that light is both a wave and a particle. That our modern view of light considers it a wavicle. That is, sometimes it's best to describe light as a wave, and other times we treat light like a particle, depending on the circumstances that we're looking at. Now, in this class, we're mostly going to be dealing with light as a wave. But a particle of light is called a photon. And you may have actually discussed this a little bit in chemistry, because most of the light we see, most of the photons we perceive, were created by the electrons in atoms. So here I have a very simple model of an atom, and you have an electron going in a lower energy level. And if I click on that electron, when it moves to a higher energy level, eventually it drops back down, and the energy it loses gets turned into a photon of light, and light is created. Now, the energy of that light is given by the frequency. The energy of a photon is equal to hf, where f is the frequency of the light in hertz, and h is a constant known as Planck's constant, which is a very tiny number, 6.626 times 10 to the minus 34 joules times seconds. So what we need to remember is that how much energy light carries is directly proportional to its frequency. The larger the frequency, the more energy it carries. The smaller the frequency, the less energy it carries. But that's about all we're going to do is considering light as a photon in this chapter. What I really want to do is concentrate on how we can treat light as a wave. So what we actually tend to refer to light is just the visual part of the larger electromagnetic spectrum. So here is the colors of the visible spectrum, starting with red and going to violet. All electromagnetic waves are transverse waves. Now, and why? Here is a very simple model of an electromagnetic wave. Now, on this picture, the light wave is actually going in this direction. So the light is traveling this way. Okay. Now, you see that as the light travels this way, there's an electric part of the wave that's vibrating in the y direction, up and down. And the letter B here represents the magnetic portion of the wave, which is vibrating in what they call the z-axis, back and forth. The important thing to note is that this electric and magnetic piece are vibrating perpendicular to the way the wave is moving, which makes it a transverse wave, just like it did in mechanical waves. we're not going to worry too much about what the electric and magnetic fields mean. We'll cover electricity and magnetism in a later chapter. So for now, we just need to understand that as light moves in one direction, in this example along the x-axis, there's something vibrating, an electric piece and a magnetic piece, that's vibrating perpendicular to how the wave moves. Now, the speed of light is very important because the speed of light, first, it's incredibly fast. Oh, let me get... It's incredibly fast. It is 300 million meters per second, or that would be the same thing as saying, see if I can get my pen in the right position. That's 3. I lost the video. Times 10 to the 8th meters per second. And you can see I'm not too used to using my tablet yet. Let me try to rewrite that a little bit clearer. Three times 10 to the 8th meters per second. There you go. That's a bit better. All right, and nothing in our universe can travel faster than that speed. Nothing in the universe can travel faster than the speed of light in vacuum. Now, as an example of how far light travels in such a short distance of time, here's a simple problem. How far away is the sun if it takes 9 minutes for light to reach the Earth? Well, light can't accelerate. It just travels at a constant speed. So the light from the sun, this 9 minutes represents time. So right here, I know that this is time, and I want to know how far away this is. So I'm looking for a distance. So I know that distance, that's a bad, hang on. I know that velocity is equal to distance divided by time. So I'm going to solve this equation for distance. I'm going to get that distance equals velocity times time. Now, in this case, the velocity is the speed of light, so I'm going to replace that v with a c times time. Now, the reason why we use c instead of v for light is just to let us know that we're talking about a very special speed. The speed of light is constant for all electromagnetic radiation, so they all travel at 3 times 10 to the 8th meters per second, so we use the letter c. But it's just a velocity, so it works the same as any other velocity we've worked with before, just as a very big number. So I know that then distance is going to be equal to, well, I have my velocity, 3 times 10 to the 8th meters per second. But I got to multiply that by t. The problem is my t is in minutes, and I need my t in seconds. So let me make a note that time is going to be equal to, well, that's 9 minutes times 60 seconds over 1 minute. I'm going to switch pen color, make it a little bit easier to see. There we go. So if you figure out the time in seconds multiplied by 3 times 10 to the 8th, what you're going to find is that the distance is equal to 1.62 times 10 to the 11th meters. Now, if I divide that by 1,000, I would get that the distance then is going to be equal to 1.62 times 10 to the 8th kilometers. the problem didn't ask for kilometers or meters, so you know, if the problem just on a computer just asks you for distance, you can feel free to use meters, unless it explicitly asks you to change it to kilometers. But all I did was divide by 1,000 there to go from meters to kilometers. All right, so let me wipe away my annotations and let's go on. Now, light waves can be polarized. Now, this is an important concept, so let me take it a little slow. So, when light is first created, the electric and magnetic fields part are bouncing in all different directions. So, you see here, this is light that is moving. This is a light ray that's moving in this direction. And the electric piece, what they're showing here is just the electric piece and how it's bouncing all around. Now, the reason why we're interested in the electric piece is because it's the electric part of light that interacts most strongly with atoms, because the electrons on the outside of the atoms are charged, and so they react with the electric fields. Now, there are certain types of materials that they're made out of long molecules that absorb the electric part of the light and block the light ray from going through. And if you arrange it properly, then only the part of the light that is vibrating in the same direction as this fence, which represents really a bit of plastic, but you wouldn't actually see the slits. The slits represent the spacing between molecules, so microscopic. So what's happening here is you have the electric field here bouncing all over the place. That means the light is not polarized. But after it passes through this filter, only the part of light that has an electric field going up and down in the direction of the filter comes through, and we call that polarized. So generally, most of the light that when it's created either by the sun or a light bulb or a glowing object, that light's unpolarized. The electric field is bouncing in all different directions. But there are some materials that will block light, except for when the electric field is going in one direction, and that light's polarized. Polarized light's actually very important. It's used in a lot of calculator displays, a lot of computer displays. So we work with polarized light a lot in our technology. Another time that polarized light is important is when it reflects off of certain objects. So when light reflects off a non-metallic surface, now the mirrors in your house are not non-metallic. Although they are made out of glass, that's not where the light's reflecting. The light's reflecting from the back of the mirror, which is coated in metal, generally aluminum. So the light coming off your mirror is not polarized. But here is a situation where a light ray is bouncing off of a frozen lake. Now, the lake is frozen water. Water is not metal, and so when this light ray bounces off the lake, it becomes polarized. So here, the electric field is going in all different directions to the left, on the left side of the image here. And then the reflected light ray, the electric field is only vibrating parallel to the ice. So again, this side is not polarized, but the reflection is polarized. Okay? Now, this reflection that's polarized, this is what we typically call glare. This is the glare coming off of perhaps a glass window of a car in front of you, or a lake on a summer day. Polarized sunglasses can get rid of this glare by using polarized pieces of plastic. So as you look at the glare, since it's polarized, let's take a look here at the this red. Let's say the red is glare coming from the surface of a lake. If I set my plastic so the polarizer is going up and down like this, so these lines represent the molecules in the plastic, this red glare is completely blocked. And the only thing that'll come through is the light that is not vibrating in that direction. Is vibrating in the same direction as the filter. So here you see the blue light going up and down. It can slip right through that filter, where the red is vibrating sideways and the polarized sunglasses block it. You also use polarized sunglasses at the 3D movie theater. When you watch a 3D movie, the reason why you need to put on glasses is for 3D movies, they have one lens polarized this way and the other lens polarized this way. If you've ever taken off your glasses in a 3D movie, you'll notice that the image looks on this, you'll see double image on the screen because what you're really watching are two movies. So to mimic how our eyes work, when they make a 3D film, they shoot two movies slightly offset from each other. So one side of your 3D glasses only lets one movie coming in this eye. The other side of your glasses only lets the movie come in the other eye. And that's how it actually tricks you into thinking you're looking at a 3D image. So you've probably used polarized glasses without even knowing it. A lot of people who have boats use polarized glasses because they drive boats use polarized glasses because of glare coming off of water.